Well, guys, we're back
Here
talking
we are.
about chemistry stuff.
More reaction mechanisms.
Kinetics. We're talking about kinetics today.
Catalysts. I like
Catalysts.
catalysts.
Catalysis.
Yep.
We're going to catalyze things.
We are.
You know, something so cool about catalysis reactions is they're very exciting.
They are. Quite. We're going to do a bunch in class for you. We're not
Yeah.
going to do them on the podcast because they're just better to see live.
If you've ever seen the pumpkin that throws up.
Oh, Pukey the Pumpkin.
Pukey the Pumpkin is an amazing demonstration. So, we will do that in our class. However, if you're out in the internet land, make sure your teacher does Pukey the Pumpkin.
Pukey the Pumpkin, Elephant Toothpaste, or the Glowing Penny.
Oh, the glowing penny is very cool. That is
Yeah.
a very, very cool demo. We'll do it in class
Yes.
for our kids.
Ask for them by name.
By name. Pukey the Pumpkin. Remember, PP. PP. Oh, mercy sakes alive. PP. All right.
And I'm the one with the 3-year-old.
I know, and I have a 15-year-old. All right, so podcast 12.3, reaction mechanisms. This is the last part of chapter 12 of kinetics and catalysis. Hey! Reaction mechanism. A mechanism is kind of a weird word.
It is.
Yeah.
Yeah, it's kind of the business end of what's going on in the chemical reaction.
A lot of people think of mechanism and think like mechanical things, and that's not exactly right. It
Sort of is.
We're using the word in a different way. You see, reactions happen through a series of
Intermediate steps. No.
Individual steps.
Okay. I'll buy that.
Intermediate steps,
Yeah.
or just steps. They have, usually when you see a reaction, you say A plus B turns into C. Well,
Right.
it turns out that's not exactly right.
Never quite
There's
that
a bunch
simple.
of steps to get to A plus B makes C, which is what we're going to learn about here. All right, now there are different kinds of steps. There are 3 varieties of steps.
Yes.
Varieties.
Yes.
Those are unimolecular.
Uni means one.
Now, uni means one. So what does that mean? That means one chemical breaks apart into something else.
Yep.
Say B plus C. So you just have one chemical. Okay. Bimolecular means you have two chemicals. So it could be like A plus A turns into B, or it could be A plus B turns into C. Now, as a side note here, this means this chemical right here, A, in unimolecular, just needs to break apart.
Yes.
But what you're looking for here is you're actually
Two
looking
A's
for...
that stick together.
Actually, they must collide.
Yes.
Or stick together. They may stick or whatever.
So they have to hit girls?
They have to hit girls. Actually, this comes back to the prom date.
Back to the prom date,
A
yeah.
bimolecular step is where one boy meets and hits one girl.
Right.
Okay. And in a termolecular state, which is actually quite rare, termolecular steps, this is A plus B plus, say, B. And essentially what you're looking for, and it turns into D or whatever, is that these 3 things must actually all collide at the same time.
And with the correct orientation.
Yes.
And the odds of that happening are very, very slim. So these tend to be very, very slow
Most
reactions.
common are actually bimolecular. You're
Yeah.
waiting for 2 atoms to collide, or 2 molecules or whatever. And termolecular steps are rare, and this is moderately rare. It does happen.
Yeah, it
You're just
happens.
waiting for a sort of an unstable atom to break apart. If you have unstable atoms, that they are made actually usually typically as an intermediate step. Okay. So, some steps are fast, and some steps are slow. So the rate of the reaction is determined by the
Slow step.
slowest step. And this is called the rate determining
Step.
step. You might think of it this way. You ever been on a athletic team and there's a relay, or you're just in an athletic team? You're really only as good as your
Weakest player or slowest member?
Yes. So that's kind of the deal, is that the rate is determined by the slowest step. So if one step is slow, the rate is determined. The rate is really that slow step. Okay? Now, we've got a couple of definitions we want to talk about. Chemicals that appear on the product side and then eventually disappeared are called
Those are intermediates.
reaction intermediates. Mediates. Or simply, actually this should go here, I guess, the way I have it set up. Or simply intermediates. You'll see what we'll do some examples in a minute. Okay? For a reaction, the mechanism must meet 2 criteria for it to be a plausible mechanism. Number 1, it must agree with the rate law.
Yeah. If it doesn't match the rate law, it's not a viable mechanism.
And it also must have the stoichiometry agree.
Right, with the overall reaction.
Yeah. We're
do
writing
examples.
a bunch of words here, and my guess is you're going, huh? But as we do examples, you'll see. So let's just kind of get these down. Well, speaking of examples, let's have at it. Here's a reaction. Right, where'd it go? Here is NO2 plus F2, or two NOs, makes this. But it turns out that the reaction is, the steps of this reaction are this and this.
Proposed steps.
Yeah.
Suggested
so,
mechanism.
Well, first of all, let's kind of talk this through.
Okay.
First of all, let's identify some things here. So there's NO2.
Okay.
This is a what type of step, Mr. Sam? Step 1.
Bimolecular.
That means we're waiting for the NO2 to hit the F2.
Yes.
And then it produces NO2F. Now, there's NO2F there, okay.
Yep.
But it also produces some F.
Yep.
I thought there was no such thing as F. I thought it was always F2.
Well, it's an intermediate, and so this is one of the things that happens in the process of this proposed mechanism.
So this right here is an intermediate. See,
Right.
folks, that's a chemical that exists for a time, and then it disappears. Because actually, if you take these Fs,
They're going to cancel
they're
out.
going to cancel out. It's very highly reactive. So F2 right here is a stable molecule.
Right.
F by itself
Not so
can
much.
exist for just a brief microsecond, but it is very unstable, but
Yeah.
it can. So we can actually, let's check the stoichiometry.
Yeah, let's
Do these two reactions essentially add up to this reaction right here? Well, to do this, the Fs we just talked about,
Go
they
away.
will cancel. And
So we've got two NO2s right there.
so NO2 here and NO2, that would make 2 NO2 plus, I see on
F2.
this say, F2,
Yep.
and that will make
2 NO2F.
NO2F. Is that the same reaction
It
as you have up here?
is. So the stoichiometry
So
matches
the
up.
stoic is correct.
But there are two criteria to determine if it's a plausible
So let's see
mechanism.
what the rate law would be for this. You always go with the slowest step. So
Right.
the slow step is step 1.
Right.
And what are you waiting to happen in step 1?
We want the NO2 to collide with the F2. So,
So
rate
is simply just going to be
K.
K times the concentration of the NO2 to the first power, because you're waiting for that, times the F2 to the first power.
Right. Now, we should also note that in the intermediate steps, the coefficients in front,
They do matter.
they correspond with the exponents of the rate law. Only on an intermediate step of a reaction mechanism.
Yeah, not in the overall reaction.
Not in the overall
Because
reaction.
notice here, we do have a 2 here in this reaction.
Right.
See, because what you're doing is you're waiting for the NO2 to react with the F2. To bond, or to collide. That's the word I was looking for.
Yep.
But it produces this F, which is very, very reactive right here. And then he quickly finds the NO2 because he hates being by himself. He
Right.
wants to, and it turns into NO2F.
Right.
So this step is zoop-a-doopity fast.
Yes.
Here's the word, zoop-a-doopity.
Yeah. Now, in order to determine if this is a plausible mechanism, we would have to experimentally
Yeah.
determine what the rate law is and compare this rate law that we just wrote from our mechanism with the slow step
Yeah.
to the experimentally determined one. And if they match, then it's okay. But we don't have that information here, so we can't say for sure if it's a valid mechanism.
But that would be the rate law if this was the valid mechanism.
If it was, yep.
And it's a reasonable one, too.
It is.
All right. All right, let's do another one. Actually, we have the rate law for the following reaction. Okay, this is actually, there's a typo a little bit. That should be 1 and 1 here.
Yep.
So we've got ClO2F2, 2 of them, plus F2 makes this. And we have 2 mechanisms. Let's kind of break this apart here so it's easier to see. Which one is correct? Okay?
Okay.
So let's figure this out.
Let's start with rate laws.
So let's start with experiment 2. What do you
Okay.
think?
Sure.
What would be the rate law for this one? Actually, let's assume, I think it's probably a reasonable assumption that they do add up to this right here.
Okay.
Maybe we should still do it. We got F2 plus 2 ClO2F2,
Yep.
and then you
It
get
works.
2. This 2 right here, I think it would be easier to write 2, 2, and 2 here, don't you think?
Yeah.
And then the
So-
2 F's are going to cancel. There's those F's again.
Yeah. Stoichiometry works.
Yeah, stoichiometry works.
Okay.
So, but you got a slow step, right?
Yep.
So the rate for experiment 2 would be equal to K times the slow step. What's the slow step?
F2.
F2 to the first.
Yep. That does not match.
Look, it says we should have the ClO2 and the F2.
Yeah, so that one's not good.
So that one didn't
So
work.
the stoichiometry matches, but the rate law does not.
So,
So,
wrong.
it's not that one.
Okay, this one is a little more complex. Here's our slow step. So I would, of course, say rate would be equal to K times the concentration of the ClO2F2 to the first. Does that match? No, that doesn't match either. Oh, but wait. Let's think this through. What is ClO2F2?
That's an intermediate.
Oh, yeah. So the ClO2F2, when you do the reaction, will cancel.
Mm-hmm.
And I want you to very carefully note that this arrow right here is not a single arrow.
No.
It's a double arrow.
Yeah.
And so what you can do mathematically, a double arrow is like an equal sign. You can say ClO2 F2 is equal, using this arrow right here to make our equal sign, to ClO2 parentheses F2.
So watch out for those double arrows, and actually sometimes these will be called not the fast step, but the fast equilibrium.
Yeah, you'll use the word equilibrium and maybe not even have the double arrow.
Right.
But if algebraically, if ClO2 F2 is equal to ClO2 times F2, we can algebraically substitute that in here, and so you can say equals to K times ClO2 parentheses F2 parentheses. And folks, that is the same as this. So number 1 is correct. And also they will also say something down here they did. Justify your answer. Actually the justification is this mathematics.
That and use some words too.
Yeah,
say,
true.
Since blah blah blah, that's
Since
the same.
this intermediate is equal to this, we can substitute, just like we've said it in words, but you should do it in writing in words. Okay, this is actually this question right here is from an old AP exam. This is so the 1985 test or whatever it was. I don't know. Okay, all right. Example 3. For instance, any old reaction in form 2A. What are we doing here? Okay, here's a sample problem, Mr. Sams. Actually, it looks a little different. Just from a second ago, we had some errors to correct. But you would see this on a typical AP exam. So we've got a reaction. 2A plus B turns into C. And we get a bunch of data obtained. And so we have a number of questions that we'd ask.
Yep.
Okay, so let's figure out what the question is.
Let's go.
Question number 1 is, what's the rate law? So this kind of goes back to that method of initial rates methodology.
Yeah, back to
and we've got A
one.
and B. Now, first of all, the rate law will take the form rate will be equal to K times A
to something.
the X, if you will, times B to the Y.
All right.
And so they're going to ask us what's X, Y. And I think they're going to ask for K too. But
okay.
in this part A, they didn't ask that.
Nope.
So I'm going to find some things that are going to cancel out.
Let's do reaction 3 and reaction 2.
Let's just number these 1, 2, 3, and 4.
Yeah.
So I like 3 here and 2.
Yep.
And I want to do 3 divided by 2 because this gives me a bigger number. So I'm going to do E3 divided by E2. So E3 is 6.0 times 10 to the minus 2 is equal to 0.50.
K times 0.50.
Okay, thank you. To the X times 0.15 to the Y.
Yep.
And then we're going to take, what is it, 3? No, 2. 2.0 times 10 to the minus 2, and that's equal to K times 0.5 again to the X times
0.05.
0.05 to the Y. Now, calculator,
Nope.
no, I don't need a calculator. This would be 3. Would be equal to,
K's go away.
the K's go away, the 0.5's go away, so 0.15, that's 3, right?
Yep, 3 to the
3
Y.
to the Y.
Y is 1.
Equals 1. That's not too bad, is it?
Nope.
I can handle a problem like that. That's not so hard.
All right.
All right, now we need to do figure out what our next experiment will be. Now we know Y equals 1. I need to find a way to get X.
Doesn't
Serious
matter.
problems.
Pick on.
Pick them. 2 and 1.
Sure.
Actually, I'll do 1 and 2.
1 and 2.
So I'm going to do experiment 1 and experiment 2. All right. So we're going to do E3.
No, we just did 3 and 2. Let's do 1 and 2.
E2
E1 and 2.
divided by E1, right?
Nope.
E1
Yep.
divided by E2.
Yep.
Here we go. All right. So this would be 4.0 times 10 to the minus 2 would be equal to K times 0.3 to the X times 0.1 to the 1, right? And this will be 2.0 times 10 to the minus 2 is equal to K times 0.5 to the X times 0.05 to the 1.
All right.
Now the 10 to the minus 2's cancels, the K's cancel, so I can say 2 is equal to 0.3 over 0.5, Mr. Sams.
0.6.
0.6 to the X times 0.1 over 0.05. I didn't calculate, that'd be 2, wouldn't it?
It is 2.
All right. So I divide both sides by
2.
2. 2's cancel, and I get 1 is equal to 0.6 to the X.
Well, that's fun.
So what's X? That doesn't come out
0.
nice. Yeah. Remember, any number to the power of 1
Yeah.
is 0. So this is an interesting one.
any number to the power of 0 is 1.
Correct. Did I say it backwards?
Yeah, you did.
I'm sorry.
Yep.
Yeah, Mr. Sams is correct. So this is an interesting one. So what's the rate law of this one? Rate would be equal to k, the x, no, it's the y, times b to the first.
Right. Because
The
a to
A.
the x is 0, so it goes away.
That's it. Okay.
The rate
So-
equals k times b to the 1.
All right. So now that we know that, let's part B says find k. So rate is equal to k times b to the first. So we'll just take experiment
Pick
1.
1.
So I'll say 4.0 times 10 to the minus 2 is equal to k times b, 0.1. So k would be 0.4. Yeah, I can do that in my head. 0.4. Now the units on that will be,
First order reaction, so that's seconds to the minus 1.
actually the 1 should be here.
Yeah.
So it's just seconds to the minus 1. If you forget how to do that, watch the other podcast.
Yep.
Okay.
12.1.
Now, how long will it take for the... Okay, to solve this problem, we're going to start with our reaction. 2A plus B turns into C. Now, we do have to do sort of something we haven't really talked too much about. As you do AP chemistry, you'll learn more about this, what we call a BCA table. This initial amount, or the beginning amount of the A is 0.3. The B is... no, I do that wrong. This is 0.4.
Yep.
This is 0.3. And this is 0.
Right.
And as time progresses, they're asking for, there's a change in the amount, and the ending amount of the C is going to be
1.
0.1. So that means that the change, or the C amount, was 0.1. So this is on the arrow, the product side, the C is. So B is going to have to diminish by a certain amount. So I'm writing a negative, and that'll be also 0.1.
Right, because their mole ratios are 1 to 1.
to 1, so this will be 0.2. And this will be minus, now this is a tricky one, Mr. Sams.
This one's going to be minus 0.2 because of the 2 to 1 mole ratio there.
But we really don't care too much about A.
No, because the rate law only
because the
depends
rate
on
law
B.
only depends on B. Now, we're trying to do a time. Now, when you're trying to find time, as you recall, the key thing is we use the integrated rate law.
Right.
Now, this is a first-order rate law reaction. And so if you recall, the rate law for a first-order reaction, or at least the integrated rate law, is the natural log, and we'll say of
B,
B,
because
that's what we care about right here, right? Would be equal to negative KT plus the natural log of B original. So our B original is 0.3. Our B at the time t is 0.2. And we know the value of k. We calculated that just a minute ago.
It's 0.4.
That's 0.4. So I will say the natural log of 0.2 would be equal to negative k. Now k, if you recall, was 0.4 times t plus the natural log of B original, which is 0.3. Well, we simply solve for t, right?
Yep, solve for t and you get 7.03. So 7 seconds.
Seconds, yeah. So that's how you solve that problem.
There it is.
Okay, there you go. All right. Now, one of the mechanisms is correct. Which is the following mechanism is correct? Well, if you recall, rate is equal to k times b to the first.
And
All right.
our reaction is
Yeah, it was what?
2A
plus b makes c.
So we need the stoichiometry to turn into that, and the...
Actually, my first eyes jumped down here because I see b by itself in the slow step. But let's work through the mechanism 1.
Yep.
This one, this slow step,
Yeah.
guess what the rate's going to be?
That's going to rate equals k times A and B. So that's no good.
That's not going to work.
Nope.
Okay. And this one, the slow step, it's b times m.
Red
Oh,
M's,
okay.
M's.
Rate would be equal to b...
No, K.
K times b times m. Now, m, that's not in the reaction.
No, it's an intermediate.
It's the intermediates.
So it goes away.
So actually, it doesn't really go. It goes away, but m is equal to a and b.
Oh, yeah.
So actually, this one would actually be equal to
A, B squared.
b times a times b. Yeah, b
Yeah.
squared. Actually, the k. So that's not equal either. And
No.
this one, rate
That
equals
works. Rate equals K times B.
k times b. Now, we got to double check, does this reaction add up to this reaction up here?
Well,
We've
our
got
M's
m's.
go away.
Our m's go away.
And the N's go
M
away.
goes away. So I got b plus a plus b
Uh-oh.
makes c.
No good.
There's something wrong with this problem, Mr. Sams.
Could be.
Yeah. So that's
So none of those are valid
b
mechanisms
plus
for what
b
we've arrived at.
plus a makes c. So, yeah, that's
Oh, well.
wrong. Oh, well, there must be a third one or a fourth one. There must be a typo, or maybe at the beginning we solved the problem wrong.
It's entirely possible.
Or we have our
Catch our
numbers
mistake.
wrong.
Let us know what we did.
Yeah, email us. Okay, but hopefully it's still instructive on how we would solve the problem.
Yep.
That's the key thing, really. All right. Hey, let's talk about the last thing here, catalysts. A catalyst. Catalysts are kind of cool. It's a substance that speeds up reaction without
being consumed or being part of the reaction.
Yeah, consumes, that I would say.
Catalysis. Does that mean splitting things by cats?
I don't like cats, so I don't want to split anything with cats involved. They make me like sneeze.
I like cats.
Water eyes.
I like
Lord
my
have mercy,
cat.
those things are horrible. At least to my body. All right. It's also a chemical that lowers the
activation energy.
So a couple things that we need to talk about in terms of catalysts. The way a catalyst works, basically it speeds up a reaction by lowering the activation energy, but the way it does it is by changing the reaction mechanism. Mechanism.
This is the matchmaker in
So basically,
how to get a prom date analogy.
Different steps.
Different?
E-R-E-N. Different. They have different steps. Different. They have different steps. And so the steps, like in this problem we just did here that had all kinds of problems, you have a different set of steps. It changes the steps. And by changing the steps, you have different amounts of energy, and it makes it faster. So here's what we call a reaction coordinate diagram. This right here, the red line, is the normal reaction, the energy barrier you must get over. You have to. This is called the activation energy right here. But if we were to do the activation energy of the catalyzed reaction, it would just be from here to here.
Much lower.
So it's much lower. Okay. All right. Another way to look at this is we can say. This is a Boltzmann diagram. The number of collisions, remember, it's all about who hits who, right? And then the energy. Only these guys have enough energy to react. But if you have a catalyzed reaction, notice that the line that was here, if it was kind of like, right here, has been moved over. There's more of them with enough energy because the activation energy has been lowered. Yep. So that's how it works. Hey, how can you see a catalyst in a reaction? Make me a match, find me a find, and catch me a catch. All right, I know that song way too well. All right,
I know. I was just noticing that. I was going to stop after Make Me a Match.
There you go. I already have a match.
You just took it to a whole nother level.
I love Fiddler. Who is the fiddler on the roof?
I don't even think I've seen the whole thing.
Greatest.
I think I watched the first half
musical ever,
and
all right,
was done.
So here we have a reaction. All right, actually these are considered the mechanism, determine the overall reaction. All right, so we've got this reaction. All right, now anybody looks like they can cancel out. We want to cancel them out.
NO2.
NO2 is here, and NO2 is here.
That's an intermediate.
So that would be an intermediate. NO is here, and NO is here.
That's a catalyst, because the catalyst is there at the beginning and the end.
And our overall reaction is O gas plus O3. That's ozone, actually.
Yeah, it is.
Makes two O2s. So this is the overall reaction. Now we've got a couple of things that we want to highlight in this.
Yeah.
Mr. Sams was saying that, and I think we should slow down and pause and make me understand. NO2 appears as a product first, and then it disappears in a cancelization. So this is called an intermediate.
Intermediate.
But we have something very different happening with the NO. The NO is starting the reaction. It is a reactant first and then disappears. The NO.
It doesn't disappear.
It doesn't. Well, it doesn't really disappear. It just isn't a part of the overall reaction.
It's there at the beginning. It's there at the end. It cancels out.
So it's still there. So
it's still there.
Catalyst.
Right. It doesn't get consumed, so it's still a catalyst. Now, side note about this reaction, NO is a pollutant that goes into the atmosphere, and it actually catalyzes the conversion of ozone, O3, into oxygen.
This is actually
that's part of the whole ozone depletion thing. Now, the thing about it is NO2, since it's not consumed, it stays there and it catalyzes another reaction. And it stays there and it catalyzes another reaction. And it stays there and it catalyzes another reaction.
I think I understood, I read somewhere that this particular NO will catalyze, they say in that order of, I want to say like 30 million reactions.
One molecule?
One molecule will do 30 million, destroy 30 million ozone molecules.
Wow.
Something like that. And then eventually it turns into something else, on average. So this is a pollutant that we pump out of our gas tanks and such.
That's why you have a catalytic converter. It turns that into something less reactive.
Actually, it turns it into
NO2.
Nitrogen.
Or nitrogen gas,
Nitrogen and oxygen, yes. Harmless things. All right. determine the overall reaction, which substance is the catalyst and which is the intermediate. So it's the same type of reaction. So let's do one more example here. I see Cl gas here. Okay, and then I got ClO gas. Okay, and this is really the same reaction.
It's the same reaction.
O plus O3 makes 2O2. So which one would be the intermediate?
Intermediate is ClO because it shows up and then goes away.
Intermediate. And which one would be the catalyst?
Is Cl.
So another reaction. This is the catalyst.
Yep.
Okay. I think, yeah, that answers all the questions there, doesn't it?
Alrighty.
All right, there are two kinds of catalysts.
Yes.
If we were to just talk about types of catalysts, the way catalysts actually work, there's homogeneous catalysts. Same what, though?
Same phase as the reactants.
Meaning they are in the same state of matter.
Yep, solid, liquid, gas.
So if I have a catalyst that's a gas, and the chemicals are gases,
that's homogeneous.
Heterogeneous. Different. A different state. So actually catalytic converters are the classic example. You have gases, and then they come across a piece of platinum, I believe it is, platinum solid. And as these gases come in here, it comes off and makes the reaction, actually takes actually the nitrogen oxides and turns them back into nitrogen and oxygen, which will not harm the environment at all. So actually it's pretty cool how a solid catalyst works. Okay. I think... No science fair projects. I think we are done with chapter number
12. Yeah.
So we should make sure that you guys get good dates.
Yes.
For the prom.
Remember, send us your pictures.
We're
going to start a prom date wall.
We need the prom wall. The prom date wall. So please,
especially if you used our method for getting a prom date.
Definitely, and I need the story. We need the email story. Just the pictures, the proof. And the story is classic, too.
Yep.
So we will see you on, in class,
Chapter
or if
13.
not, in Chapter 13. Bye.